cold dark matter is, you have to postulate the particle. And a good candidate is the so-called axion. And the axion is very well motivated. One of the problems with the standard model of particle theory is that the electric dipole moment of the neutron is experimentally measured to be at least 3 orders of magnitude below the prediction of the theory. And by postulating the axion, you can fix this problem. So we know from these measurements of the background radiation that the density of cold dark matter is about half a GeV per cubic centimeter, so these are obviously in energy units. The predicted axion mass is thought to be between a microvolt and a millivolt, with most bets being on the lowest decade. And that corresponds, when you convert mass to frequency, to a quarter of a gigahertz to a quarter of a terahertz. And if axions exist, we're all filled with them. For a mass of a microvolt, the density of axions is about 10 to the 15th per cc. So how do you find this very light particle? The basic notion is that you rely on something called Primakov conversion. And the idea of that is the following, that if you have an axion in a high magnetic field, the theorists tell us that it will decay with some calculable probability into a photon with a photon frequency equal to the mass of the axion. And also, in fact, you have a virtual photon to conserve angular momentum. So the detector consists of a cavity surrounded by a superconducting magnet. And the idea is that you would like the photon frequency to correspond to a mode of this cavity, so that it would be on resonance. So on the right-hand side here is the power in the cavity versus frequency. And if you're off resonance, you see the noise in the cavity, and here's the glitch, and that tells you found the photon corresponding to the axial decay. Now, in the original manifestation of this, the photon field in the cavity was detected by an antenna coupled to a HEMT, a high electron mobility transistor. Now, before we go on, here is a photograph of the axion dark matter experiment, ADMX, and the cavity I've just been talking about is at the bottom end here. So this is lowered into a large dewar of liquid helium surrounded by a superconducting magnet, and the original experiments were 1.5 Kelvin, and the magnet was 7 Tesla. Now, to make a complete story here, I need to dwell for a moment on the concept of amplifier noise temperature. So here's an amplifier with a gain of -A, and across the input terminals we've connected a resistor of resistance R at an input temperature Ti, and at the output from the amplifier we see an amplified version of the Nyquist noise, or the Johnson noise, in this resistor. And if you look at this spectral density, that is the power in the output, here's the Nyquist noise term, 4K Boltzmann T input times R, but we've added to that a term T sub n for noise temperature. And that is the added noise of the amplifier. And it's a very simple, very convenient way of characterizing the noise of amplifiers. And as you can see here, you simply add them together. The quantum limit of such amplifiers is given by Planck's constant times the signal frequency over Boltzmann's constant. So in the original detector, the noise temperature of the system Ts was equal to the cavity temperature plus the noise temperature of the HEMT, and those add up to give you about 3.2 Kelvin. Now, from the predicted properties of the axion and the known properties of the detector, you can calculate the time to scan from a frequency of 1/4 gigahertz to 1/2 gigahertz. That is the lowest octave of the predicted energy of the axion, and it's given by this calculated number times the system noise temperature squared times 1 over f1 minus 1 over f2. So you can calculate all that, And what you come out with, unfortunately, is about 3 centuries. That is a problem. It is difficult to convince funding agencies to fund this on an ongoing basis. It's very difficult to recruit research students to work on it. So at that point...
Long-term project.
I'm sorry?
Long-term project.
Long-term project, yes. So at that point, I was recruited again to see if we could do better with a squid amplifier. And without dwelling too long on this, here is the conventional squid that I've shown before, and you normally apply the signal between the 2 input leads of the coil, and the current around the coil couples flux into the hole. The problem with this is that as you start to go up to 50 or 100 megahertz, the capacitance between the coil and the washer starts to roll off the signal. We actually solved this by moving one wire, so that we now apply the input signal between the washer, the blue washer here, and one end of the coil. And bearing in mind that the coil is separated from the washer by a capacitance, I hope you can see now that what we've made is simply a transmission line. And if you launch a signal at the beginning here, if you have a half wavelength on the line equal to the length of the line, then you expect to see a large resonant coupling of the signal into the squid. And indeed, that's what you see. This, in fact, was the first set of data that we published. Here we're plotting the gain of the amplifier versus frequency for 4 different coil lengths. And what you see is that as we progressively decrease the length of the coil, as you would expect, the resonant frequency moves up. And in this particular case, we've got something like 18 dB of gain at 650 megahertz. Well, we've made various versions of these over quite a few years, and I just want to show the result for the current version that we've made to demonstrate the noise temperature. So along the horizontal axis, I'm plotting the bath temperature of the squid, and along the vertical axis, I'm plotting the measured noise temperature, and both in hundreds of millikelvin. What you see is that as we start to decrease the temperature, the noise temperature decreases linearly. And this is because the noise in the squid is generated by Nyquist noise in its resistive shunts. But eventually it starts to flatten out, and as you can see in the inset here, it in fact flattens out at a level somewhat higher than the quantum noise temperature. The quantum noise temperature should be 30 millikelvin, and the temperature measured here is about 1.5 times this. So this device is within a factor of 1.5 of the quantum limit, or if you prefer, of being limited by the Heisenberg uncertainty. Just as a quick comment on this result, you can say, why is it better than a HEMT? The thing about the HEMT is that because the power dissipated in it is quite large, the HEMT itself probably operates at around 20 Kelvin, no matter what the bath temperature. So as you lower the bath temperature, the noise temperature of the HEMT does not change significantly. On the other hand, in the case of the squid, because the dissipation is very minimal, then although there might be some small heating effects around 50 millikelvin, the fact is the temperature of the device keeps plummeting as you reduce the bath temperature. Well, finally, what is the impact on the axion detector? Remember that the original axion detector had a system noise temperature of 3.2 Kelvin. If we take our measured squid amplifier noise temperature of 50 millikelvin and assume that the next generation of axion detector will be cooled in a dilution refrigerator also to 50 millikelvin, that means the system noise temperature will be 0.1 Kelvin. And the impact on the scan time is dramatic. Since the scan time gives us a square of the system noise temperature, our 270 years is reduced to 100 days. So that you can see, by introducing this nearly quantum noise limited squid amplifier, you can turn a project that was, for all purposes, dead in the water, to a project that is actually very viable. So, just to sum up on this, a couple of years ago, an MSA was operated on the Axion detector still at 1.5 Kelvin to demonstrate that it would work as advertised. And I have to tell you that the single biggest challenge was figuring out how to operate the squid in a field not of 7 Tesla, but a little bit outside the field of maybe only a couple of Tesla. But that was solved. And something like 88,000 data sets were required. The Department of Energy was thrilled. It has now funded the installation of a dilution refrigerator to cool the cavity and the MSA to something like 50 millikelvin. And this will enable an effective axion search over the energy range of about 1 to 10 microvolts. And it's hoped that this will start in the latter part of 2013. I might also point out that the axion detector originally drove the development of this near quantum limited squid, but it's finding out other applications as well, including, for example, dispersive readout of squids. So that's really the end of my story. People sometimes wonder why I'm still working with squids almost half a century later. And I think the reason is not just because of the squids, but because of their diversity. And squids are used for so many different things, in physics, in chemistry, in biology, in medicine, material science, geophysics, cosmology, quantum information, and so on. And so each one of these applications presents a new challenge, but in all of these cases, under appropriate circumstances, then the squid gives you the best bet. They're very broad-band. They're used down to 10 to the minus 4 hertz in geophysics, up to, say, a gigahertz, or even higher now in axion detectors. And at the lowest temperatures, the resolution of the squid amplifier, properly designed, could be essentially limited by the Heisenberg uncertainty principle. And the two things I've talked about, the SZE and the axion search, not to mention many other applications, are absolutely enabled by the very low noise of the squid. Even though this might seem a terribly small part of, say, the axion detector, that's what makes it tick. And the axion detector would be long ago dead and buried without the squid sensitivity. So thank you all for listening.
Thanks, John. Now the session is open for questions. Yes.
Has Axions observed or any indication they observed these experiments or these prototypes or those things? So, any indication this Axion has been observed or not?
No, not yet. I mean, it will be, as I said, late next year before the system is really on the air. I mean, it's getting built, but installing this large thing on a dilution refrigerator, which is under contract, being built, is quite a large project. It's not a cheap project either. So it's going to be a minimum of 18 months before this is really on the air.
Other questions? I have actually one. You have presented problems that are quite completely solved. To such a large community of people who do materials, unconventional treatments, can you tell us about some problems that actual skills cannot really solve? And how to drive?
Oh, they can't possibly be anything.
No, I mean, actual speed says that what's worth investigating, pointing at for new materials.
So, I think the high TC squid story is not over. And I think that many of us worked very avidly on them in the 1980s and 1990s. I think there are two problems which I suspect are still solvable with high-T squids. One is the lack of a really good reproducible junction. And I think, having said that, a lot of progress has been made with grade bounded junctions and ramp junctions. But I think it's fair to say there isn't really a technology on the level of the Niobe technology. I think the other thing that still remains to be solved is the one of flavonoids, flaxonoids, squids. And that apparently arises when you have multi-layers. And I think that if that would be solved, then it would open up more applications of squids, for example, in medical applications, certainly for magnetocardiology and maybe for magnetoencephalology, because you get high TC squid closer to the skull. So that, in my mind, are two things that really need to be done with high TC. I think that Harold Weinstock, who's director of the Air Force of Research, has funded an enormous amount of squid work over the decades. And he has this motto that says, never use the squid if something else will do it. And I think that that's a very important point, that squids are not the panacea for everything. That people can be tempted to use the squid because it's sort of fancy, when actually they can do the same thing with a simpler kind of device. Using squids in high magnetic fields is a challenge. One of the nice things about these incredibly small scanning squids is that you can operate them in higher fields. I think the sort of high frequency applications of squids will grow. Irfan Siddiqui talked earlier today about using other dispersive readouts of squids. I think that this will get squids readily into the sort of 10 gigahertz range with essentially quantum limited performance. I think this will open up new applications in general in high frequency detectors, in particular looking at various kinds of quantum detectors.
Thank you. There is another question.
Dear Professor Clarke, one question.
Sidorenko, Institute of Nanotechnology, Education, Moldova. Here, a lot of people who deal with superconductivity and magnetism. Maybe some words about the future possibility to use the pi script. This is the last decade very intensely investigated. And what your opinion about the future of this branch of things?
Right. Well, I think an obvious answer to that is in qubits, because flux qubits really operate as a squid of some kind, and if you can actually put an extra pi phase shift into that loop, that's very useful, because you can then operate it at the device at the degeneracy point without having to apply a magnetic field. So that's one obvious thing that immediately springs to mind.
Other questions? Yes.
If tomorrow I go back to my lab and I decide to make a slug, what are the chances of success?
Oh, 100%. No, I mean, people always ask me, how many of them work? And I would say that I would typically make 6 at a time, and I would cool them down. And probably 5 of them would have a usable critical current. And 3 of them were probably good enough for devices. So I have no doubt that if you went back to your lab and made these, they would work. And I think for many years, and maybe even today, these were quite widely studied in undergraduate labs. That the students would be given a piece of niobium wire and a soldering iron and some solder, and they'd make a slug and it would work. And I mean, they'd shine microwaves on it and look at the steps. The mystery is, why does it so often have only 2 junctions? And this has never been satisfactorily explained, not least by me. The basic idea is that you have this wire going through the solder, and you have a penetration depth on the inside of the sole and the outside of the niobium. So there clearly is a region that is penetrated by the magnetic flux. And if you calculate the period of these oscillations, I mean, within factors of 2 or 3, it's consistent with that picture. Why there are only 2, or occasionally 3 junctions. Occasionally I would see a 3 junction in the clearance pattern. I never understood. It's just one of those lucky things. But I promise it will work. Let me know.
Okay.
It's guaranteed.
Okay. If there are no other questions, that probably we can discuss in the very last discussion. I would really like to thank John Clarke again for his speech.